So good evening. So I'm Biagio Cosenza, and I'm senior researcher at the TU Berlin. So I'm going to introduce you my current research on automatic tuning applied to compiler, and by using machine learning. So in general, I work on high-performance computing, but also embedded system. I'm currently affiliated in an embedded system architecture group, but I'm more a software expert, so I work more with compilers. And all the things you will see I will present you today have been presented, most of them in other presentation in paper we published in collaboration with other researchers from the TU Berlin, in collaboration with the University of Innsbruck. In particular, one work was in collaboration with the University of Stanford, with Stefano Hermon from the machine learning group, and the Leibniz Supercomputing Center. So I will show you first, I will give you an introduction. What is this automatic tuning? Why we need it? So it sounds like a new problem, or it is really new. It is a old problem. The problem of selecting the best code transformation for a given code. And I will explain you why it makes a lot of sense to do it with machine learning, but also why it is challenging. The machine learning we need here, it is very different from the machine learning we commonly use for image recognition, for instance, or speech recognition. The context is different. We need very specific techniques. And what I like is to explain things by example. So I will give you an overview of 3 of my work I did by using classification, regression, and the newest one use ordinal regression, where we optimize different code by using different optimization infrastructure. So using machine learning. And to conclude, I will show you just a few notes about what I think is really challenging and interesting in this field, and also how important are the programming model in this picture. So let's start with a very simple case of tuning. So this is a simple loop, simple C loop, and one possible optimization we can do, one of the simplest optimization we can do on a loop like this is loop unrolling. So I guess most of you know what a loop unrolling is, but so suppose to apply unrolling factor 2, so our loop becomes something like that. So loop counter, in this case we increase with 2, we do half of the iteration, but the body is unrolled twice. This is a very simple optimization. That's one of the simplest. And it's also something that's not very complicated. Loop unrolling, either you don't do it, or if you do it with very small unrolling factor, like 2, 4, 8, maybe 16, no longer. So, and this optimization, it works because it improves the instruction level parallelism of the code. It is a very simple transformation. So the transformation space, so the number of possible options I have is rather small. So 0, 1, 2, 4. So overall, let's say I can take one of 6, 8 options. So the transformation space is very small. But this is a case where it's very hard to predict what is the optimal unrolling factor. And there are some work on this. So this is a first example where we need some kind of tuning for something that looks very simple, but actually is not. So predicting the unrolling factor, so predicting which unrolling factor, so how many times can I unroll this loop, and providing me the best performance, this is really challenging, and we only have very small space. Transformation space is very small. There is a beautiful paper from MIT, from Stevenson and Amorasinke, published in CGO 2005. So in my slide, I usually like to provide the source to paper. So if you want to know more about what I'm telling, just Google for the paper. You will find the paper. Like in computer science, you always find the paper online, and you can know more. But this is a more complicated example, and this we will see in details later today in this presentation. So this is pseudocode of a stencil computation. So suppose this is a 6-point Neumann stencil. So what is a stencil computation? Suppose you are working on a picture, or in this case on a grid, so in 3 dimensions. A stencil computation usually is a pattern. So it's when you write one point according to a static pattern. So for instance, in this case, we iterate over the time. So we repeat this multiple times. We iterate for all the cells in a grid, in this case, and we practically have a shape. In this case, it's a cross. The shape is a cross. You can, if you look at X, Y, and Z, we actually have a cross in 3-dimensional space. So practically, what we do is to read for the previous iteration all the point in a cross and write in the center point. So this is a very simple stencil computation. In general, we can have different variations of stencil computation, but the general idea is that for each time step, we write in one point and we read from the previous time step in different points. It may be a line, it may be a cross, what is called a von Neumann stencil. It may be an hyperplane. This is a very common pattern. You can find this in partial differential equation, in image processing, Jacobi kernel. So it's so common that people only study this problem as a stencil computation because you find it everywhere. And if you can optimize this problem, you can use the same solution for a really wide range of problems. But this problem is so well studied, but suppose I want to optimize a code like that. What kind of optimization I can do? So this is not just about loop rolling, because I can do loop rolling here, but there is much more potential. I can apply blocking, for instance, or tiling. Maybe you know this optimization under the name of tiling, which means that practically instead of going for each single cell, I go for a tile, a 3-dimensional tile or cell. No? I really read the input in block. This works for pictures, this works for grid. No? In case of picture, what you do is you have a picture, you process a tile of this picture, a subset of pixel, like a square. You do your computation there locally. Then you go next to the next one. So this improves locality, and this is particularly good if we are processing the loop of this iteration of this stencil, which are independent, in a parallel context. For instance, if we are doing multi-threading. Okay, so we can do blocking, we can do a rolling as well, we can parallelize this code, and when we parallelize, so for instance for a CPU, the 2 forms of parallelism we all use are multi-threading and vectorization. Okay, so multi-threading means that I give a chunk of thread to multiple threads, they do their computation in parallel, and stencil computation is a parallel problem, so it's very easy to parallelize. But I can also do SIMD vectorization. So this is probably this is a form of parallelism which is exploited by the architecture when you have vector instruction doing, for instance, a multiplication. You can do, for instance, 4 or 8 multiplication at the same time on vector register. So now we have 3 optimization, and all of them expose some parameter. So blocking actually we have three parameters, because blocking it means you have your grid, you split in subgrid in block, which may have a different size on the x, y, and z axis. And the size is very important, because usually the size of the blocking matches some hardware features like the L2 cache. Then we have the rolling factor. Then we have the parameterization exposed by the parallelism. For instance, how many chunk, how many seed word do we assign to each thread? This is also important because it provides a way to balance memory with computation. We can give more computation to the same thread or less, and so all of this is very complicated. Is very complicated, and in this case, this transformation space is much larger. So we have for this work I used a source-to-source compiler. We had about 60,000 configuration as a combination of all of those, and those are also pruned configurations. So it means that I really removed the trivial, stupid optimization configuration. I only focus on the most important one. There are 60,000. So do you understand? This is is a very challenging problem for tuning. How can a compiler predict that? It's very hard, and the transformation space is larger, but it is also more complex because there are discontinuities in the space. So it's very hard to find the optimal solution. And unfortunately, this is not even the worst problem we have. So here I reviewed some paper in this topic, and here there are the paper reference. But for instance, there is one research group from MIT. They did a study of, actually from Edinburgh also, they did a study of the GCC flags, all the possible flags you may use for a given code. And the transformation space is 10 to 806. Okay, but to be honest, this is a number that doesn't say anything about the discontinuity. Maybe some of them are very trivial. Actually, they are. And that's why my stencil work had a much smaller space than this other stencil work, but I think we do the same things. It's just I pruned the space. So those are big numbers. They can be pruned, but still it's challenging. Still is very challenging. So this is the first question. We need automatic tuning. And another important thing, all of those are, except probably for the GCC example, are parallel framework. This complexity in tuning comes now with the multi-core and massively parallel architecture of today, we have today, and we didn't really have paths because optimization like tiling in a single thread context doesn't really pay a lot. But when we have multiple threads working all together, then this tuning is very hard. Okay, so automatic tuning now is very important. It's becoming important and will be even more important with multiple level cache, hardware becoming more complex, having more and more core, because then it becomes very hard to understand how to tune our software. So this is to give you probably an overview why we need automatic tuning, because there are problems where it's very hard to understand which optimization, which parameters to apply for a compiler optimization. So this is the context. But in general, we would like, so there are many possible solutions, but we would like also something that what we will call an auto-tuner. So a tool that takes one of these problems, tries different combination, and in the end it provides me a very good one, possibly the best one. So we would like something that is fast, because we would like to do an evaluation that is fast, possibly to be integrated into a compiler. So as you know, when we compile a code, we want to compile it fast. So you know, LLVM, for instance, had a basic block vectorizer. They now is deprecated. They are removing it because it was taking too long. So compilers cannot take too long to take a decision. So you may have particularly compiling doing, for instance, iterative compilation. That's fine, but the standard build of a compiler has to be fast. And we want also accurate solution. Of course, we want best performance if possible. Also flexible, because we would like to have our solution to adapt to different input problem. And portable. This is very hard because usually it is possible to design very accurate solution for specific hardware, but when we move to another hardware, they do not work anymore. So having all of those is very, very hard. And traditionally, there have been two approaches. So one is to use analytical model, which are either too generic, therefore not reaching peak performance. Sometimes you can write very accurate analytical model, but you have to know the hardware very well, and your solution is not portable anymore. So analytical model, especially for wide transformation space, are very hard to build. And the other approach is iterative compilation using, for instance, search heuristics. So this is an approach used a lot in research. It's actually something like, okay, I have no clue which one is the best solution for my problem, but I will start to find one, then another one, then another one, and doing this iteratively. It means I compile, I run it, and I see the result. I compile a new one, I run it again, and I see the running time. And by using, for instance, genetic algorithms, after a long time, I mean hours or days, depends on your problem, you will end up with a very good solution. So, of course, this is a solution that doesn't work for common compilers. But this is actually the best way to have a good solution for this problem. The approach that I'm using and will show you in this presentation is using machine learning, and in particular supervised machine learning. So the idea is I have this problem. I want, instead of spending all this time when I have a new code to try all of those configurations, I will have a training phase where I test different codes and I build a model. Therefore, once I have a model trained for a machine, for a given hardware, I can reuse it later for a new input. So this works very well with compilers because I move the complexity in a pre-processing phase, but when it comes to compile a new code, a new unseen code, I just infer the model. I just make a query into the model. It's something like, okay, this code, I have seen something similar before. This is the best solution for this kind of code. So this is an idea works very well with compilers because the complexity doesn't happen at compile time, but before in a pre-processing stage. So this is a very good point for machine learning in this context. And so it's, to some extent, it's portable because if I have a new hardware, I do the new training on the new hardware, but then it will work with any code. So this is the general idea of all the machine learning based approach for compilers. And it is makes sense, makes really a lot of sense, but well, machine learning is very trending. We know it works very well for image recognition, speaker recognition, NLP. Everyone is using machine learning in those contexts. If you are talking with someone doing image recognition, you do not have to explain why machine learning works. They're all using machine learning. But it is also true that these contexts are very different requirements, And there are something that are really unique challenge. So to start, we do not have a lot of data, and in general, we don't like to have methods that requires a lot of data, because if we have to create a new model for a new machine, we have to do the training again. So if we have, this means that the whole data set cannot be used anymore. In general, we don't have huge data sets. This is the big difference with, for instance, with image recognition. Image recognition, you can download the 1 terabyte picture from ImageNet or Yahoo database, whatever, and then you can train your model. Here, this is not possible. It in general is the data, the training data for our problem. That's harder. This is one of the biggest challenge of the problem. So that's why deep neural network here. This is not really the best scenario for deep learning. And also the structure of the input, the structure of the code we are optimizing is very different. Code is not pictures, and this means we have to adapt our approach to the context. So we really need fundamentally new approaches, and this is what my research is about. So apply machine learning, but not just using known machine learning algorithms, but try to design new algorithms that are specifically designed for compiler or software optimization context. So in general, how does it work? We have a tuning problem. It can be one of those I showed you before, and we have a training phase where we encode both input and tuning configuration in a vector representation. This is something you do with any machine learning approach. So if you have as an input parameters like loop and rolling size, this has to become an element in a tuning vector. Your input can also be code, so then you need a way to translate code in numbers, in features vector. Then you fill all of this data, with all of this data you fill out a training data set, and you build a model. Okay, so there are many ways to build model. I will show you different ones today, but then we get a model. Then later, at execution or during the execution or compilation phase, so it depends on the scenario, we get a new unseen instance, and with this new instance we'll have different possible tuning configuration, and we query the model to understand which one is the best one. Okay, so how, this depends on what model we are using, but this is overall the general approach we use when we use machine learning for software optimization. What are the challenges? So there are 4 major challenges. So the first comes from the application. So we may have compiler transformation. We may have domain-specific languages, which is also a very interesting scenario. For instance, for the stencil computation I showed you before, we didn't use a normal compiler. We used a domain-specific language and a source-to-source compiler, which later generates C code. So this is very good when you already know some assumption about the input. For instance, you already know that you can make it parallel with multithreading. Domain-specific languages are very powerful because it restricts a lot it requires minimal analysis. So and you can usually make better optimization if you know the structure of your problem. But we may also have high-level application tuning, so we can also tune application choice. Which algorithm can I use for my framework? This is also something you can tune. So this is the first challenge. Then we have to encode our problem, and this is also very interesting because we can encode just a rolling factor, but we can encode tree. So if my input is an abstract syntax tree, the one used by Clang, this I can encode this in my code, and then this of course is much more challenging. I can encode graph like LLVM control flow graph, or if I use the polyhedral model, for instance, so like the one used by Poly, which is a plugin I think now is moved into the main trunk of LLVM. So in that case, if you want to use auto-tuning, to apply auto-tuning to this specific scenario, which is loop optimization mainly, then you have to encode polyhedron, so matrix. So this is another challenge. So we have to understand the structure of our input. We need data to build our model. So sometimes you don't have enough data to build a good model, and sometimes what you have to do is to synthetically generate the training data. It's like you have a program that generates stencil code or loop, and then out of this you can test, you can generate more training data. And you can also improve the modeling by doing training space pruning. So you know some optimization, they rarely have work with these parameters you put away from your transformation space. And finally, this is something I think is really new. This is something I will show you something about that. I have one work on this. We can do better modeling. So we can use what is called structural learning, so that my machine learning is designed to adapt to the structure of the problem. So this is I think the hardest challenge in this picture. But overall, those are all the problems you have to solve when you want to apply machine learning to a software optimization scenario. And I will show you 3 examples. So I will show you 3 examples of work I've been working with different compiler infrastructure using different approaches like classification regression and ordinal regression. So from the simplest to the most complex, so that you can understand what are the challenges of this. So I like to explain things by example. So the first example is what is called automatic heterogeneous task partitioning. So this is a problem. This is the problem we have when, for instance, we have the same machine, a CPU and 1 GPU or 2 GPUs. And then we have a parallel program supposed to be written in OpenCL. So maybe you're aware of OpenCL, it's a programming language, parallel programming language. It's like CUDA, but it also works on multi-core CPU. And then you have this program, this task, and you want to understand, okay, do I run it on the CPU or on the GPU? Or maybe I can run half of the CPU or half on the GPU. Okay, this is a very interesting problem. And it also applies, so this actually is an old work, so the hardware is very old because this is a paper we wrote in 2013. But so this is a work that had many citations. It has been re-implemented for different platforms, also for embedded systems, because actually you have the same problem in your mobile phone, because you may have an ARM CPU and an embedded GPU, and maybe you have a big little R. You have big and little core, big core and little core, and you want to understand this is a heterogeneous platform, and any heterogeneous platform has this problem. Where do I run my stuff? So we did some tests. It was very interesting because this is a linear regression code, and we ran it with different sizes. We ran with 1 CPU, with 1 GPU, with 2 GPUs, and also some hybrid combination. And what was very interesting is that with small size, so the size is very important, because if you have a small kernel, of course, it's faster on the CPU. When you have a small kernel, and you want to run it on the GPU, you have to move your data to the GPU. So you have to go through the PCI bus. This takes time. So small kernel is faster on the CPU. But when you have a bigger kernel, so when you have to compute this linear regression kernel for a huge amount of data, and then of course the best performing solution was by using 2 GPUs. So you really understand here, same hardware. It was an hardware with 2 AMD Opteron, and which I've seen as a single CPU in OpenCL, and 2 Radeon GPUs. And so we saw in the beginning, this is same hardware, same code, but different size changed a lot. So then we tried with a different code, and this was also interesting because same hardware but different code. It changed because the best performing in one case was hybrid, and the other case was 2 GPUs with a big enough size. Also, the CPU was very good for very small size for the regression kernel, while the Dershowitz was a bit bigger in this case, with the reduction kernel. So it depends on the code also. So it depends on the size, but it also depends on the code. So there are programs, so what I'm telling you that there are programs that requires a different partitioning. It's not said the 2 GPUs is the best solution. Even worse, if we change the hardware and we have same code and same size, same code, but different hardware. In this case, we compared the Opteron case with another machine with 2 Xeon and 2 NVIDIA GeForce. So, as you can see, results are completely different. So, this is a very interesting problem. We wanted something portable, but we know that the problem depends on the code, on the hardware, and on the size. So, this for me is really challenging. So this is a kind of problem that think about writing an analytical model for that. You don't know where to start. It's very hard to write a simple heuristics that works for this. And also we will like to support also hybrid partitioning when you, for instance, have part of the work on the 2 GPUs and part of the work on the CPUs. So this is a perfect scenario for machine learning. And we use this we use a source-to-source compiler called the Insieme compiler. I did this when I was working at the University of Innsbruck in Austria. And actually what we did was to have a training phase where we had many codes. From those codes we were extracting some features. We'll tell you in details what those features are. We were collecting those features and building a database. Then training a model using machine learning. And deployment time, when we have a new code, what we do is to extract the feature from the new code, use our model to understand what is the best partitioning, and quickly say, for this code, the best partitioning is 2 GPUs. Okay, so this was a very good case for machine learning, and we use classification. Classification, probably you are already aware of this, but classification means that all the execution we classified in our case was 21 classes. One class is, for instance, everything on the CPU. Another class is everything on one GPU. Another class is, for instance, use only the 2 GPUs but don't use the CPU. So this triple represents a class. We had overall 21 classes. For instance, these classes means 20% on the CPU, 40% on the first GPU, 40% on the second GPU. So what we did is to run each code with different sides, with all of those 21 partitioning, and mark the best performing one. So the model, the classification was select the class which is best performance. And we used both supervector machine and artificial neural network. We collected 24 static features. So this is a implementation detail, but maybe interesting. So this compiler we were using has an independent representation. It's called Inspire. It's parallel, so it has parallelism on it. At the time, was one of the first compiler having it. For instance, the feature are number of branches, number of OpenCL built-in, number of scalar floating point operation. Plus, because as we have seen, also the size is very important, we had some dynamic runtime features. So we had what is called a runtime system, and this runtime system was collecting dynamic features like the sides of the read and write, and this is very important when you send data or receive data to the GPU. So overall we had 24 plus 9 features. We applied principal component analysis on the features. So I'm assuming if you know about machine learning, you know what I'm talking about. Is just a detail, but it improves the performance. And we had 23 programs. Each has been executed with different sides. So more details you can see in the paper, in this paper. We are currently reproducing this work with SQL, which is an OpenCL-based programming model. C++, working on a purely LLVM-based compilation infrastructure. So this is our work. We are still working on this. And here are some results over 23 code. Practically, we had on one machine 86% of accuracy. On the other one, 88% of accuracy. It was working well for most of the code. There are few code like this Pendulum in one machine didn't work very well. Unfortunately, this may happen, but the problem is you want to optimize most of them. It worked very well for 86% of the code. We were really happy about that. It was much better than any other existing approach. So, and what is very interesting is that the approach is portable. We had two machines, very different machines. We knew nothing about the details of the machine. We just applied this on source code, feature extraction of the source code, and few more runtime features, and it worked. What is really interesting of this work, and this is the thing I like it more, because people, when you use machine learning, especially in this context, they tend to think, oh, but you're using machine learning, you're using this like black box, you're just applying something used in other contexts, you don't get any insight out of it. But actually that's not true. So we did this many analysis, and I suggest you to have a look at the paper, at the paper for the details. But we used this greedy feature selection to understand what was making this technique working. So we had all of those features, and we practically did this simple algorithm. We have all those features. We remove one features, and we test the model again, and we see if the accuracy, how much the accuracy decrease. So in this way, if you do this for all the features, you can understand which features were very, very important. And what was very interesting is that we had, for the two hardware, so on the left you have the best feature for the first hardware, the one with the Opteron and the Radeon. On the right you see the best feature for the NVIDIA Intel configuration. So they are different. So the machine learning approach used, for instance, for the Intel NVIDIA machine, it used the number of branch. It considered much more important as a feature the number of branch or the number of scalar floating point operation. While on the other side, for the AMD Radeon configuration, the number of OpenCL built-in function was very, very important. So this information, if I have to design an analytical model, I have no clue where to take those information. So those information are the results of applying machine learning and then doing analysis on the accuracy, on the results and on the features. So this is very interesting because this is also needs. Now, if you don't want to use machine learning, but you want to build an analytical model, then from this, you have to use those features if you want to have an accurate model. So this is very interesting, and this is the first example of machine learning using classification. And in general, classification means I have few classes, one for each transformation. In this case, a class was a partitioning, but it can be an unrolling factor for loop unrolling. And I have to select one of them. Okay. Now I'll show you the second example, which is about vectorization. Are you familiar with vectorization? Yes? No? So if you want to try it, that's very simple. Keep a loop like this in LLVM, compile it with without optimization, so minus O0, and with minus O3. So I will give you the slide, so you can also click on the Godbolt link, so you can really try this code. And you will see the generated code is very different. And so this is LLVM Clang 5.0. You will have a scalar operation using still vector register, but scalar operation if you don't use any optimization. And you will have instead a vector packet instruction. This move ups, the PS is for packet instruction, using instead the O3. So what it's doing here, LLVM is applying unrolling and vectorization. And this loop counter is 16 in this case, and it's 1 in the other case. So this is what LLVM does. So vectorization means iterating this loop every 16 times, because it's doing probably 4 for the vectorization plus 4 for the loop unrolling. So this is something that really works very well in LLVM. So we have it in GCC, we have it in ICC from Intel, we have it in LLVM. So the basic idea is, let's go from the scalar code to the vector code using those packet instruction. And so there are mainly two approaches. Now I show you loop level vectorization. There is another form of vectorization, it's called superword level parallelism. It's not really, so this is something current compiler, including both GCC and LLVM, aren't really very good on this. But it's a form of vectorization that is used when vectorization doesn't work. So what is the point with vectorization? So there are two challenges. One challenge is to understand when you can apply vectorization. If sometimes you have dependencies in your loop, in the case of loop level vectorization, and you cannot apply vectorization. Sometimes, like the loop I showed you before, you can. So we didn't study this problem. This is a problem, a very interesting problem actually. I think LLVM is very good in this, in understanding where vectorization is allowed, and is improving. We focused instead of in another problem, when vectorization is beneficial, because it may happen that I do vectorization, but the vector code is lower than the original code. For instance, this may happen if your data is not aligned, or you cannot use the full vector width, and there are some extra data movement between scalar and vector register. So there may be overhead in your code. There may be dependencies. There are many reasons that may make your vector code very slow. And unfortunately, this is something current compilers aren't really very good. So we focus on this problem when vectorization works. So on the modeling, and we find something very surprising. So this work is carried out by Angela Paul, our PhD student, and she practically hacked a big LLVM. She tried the same also with GCC, and practically she worked on the cost model, and on the cost model is this part of the LLVM vectorized, evaluating the cost of a vectorized code and the code of the scalar code. And the idea is very simple. If the vectorized code is less expensive than the scalar code, just do it. We rewrote this in terms of speed up, and we tested a known test benchmark. It's called TSVC. It's a test benchmark used for vectorization. It has something like 200 loops. And we discovered that all existing compilers over-approximate this cost model. So this means that you see those pictures. So you have LLVM loop vectorizer, LLVM super word level vectorizer, and GCC. So GCC, we show only one picture. There is a reason, because that's GCC has a slightly different approach for vectorization. But we could still derive the speed up. On one axis you see the estimated speed up, and on the other axis you see the measured speed up. So ideally we would like to have each of these cross, which is a code, one of these code in the test benchmark, on the line. But they are all lying on this side, so most of those codes are over approximated. So we find a problem, and this problem means that there are some codes for which all those compilers have a misprediction. If you see the gray area, all the code in the gray area have a misprediction, because in this case the estimation, it doesn't estimate a speed up, so it estimates a speed up of about 6, but actually there is no real speed up. In this case, it's the other way around. It is measured as speed up, but the cost model doesn't find it. So all the points in the gray area are codes that, for which the vectorization fails. Fails because it's applied, but it shouldn't, or the other way around. So false positive or false negative. So what we did for this work, so unfortunately I cannot provide too much detail about this work because it's currently under revision, but the idea is to model this problem as a regression problem. So machine learning, regression. Regression means we don't have classes, we have a number to predict, and our number is the speed up. So we practically we take practically those information at basic block level. So we look at the so we have our loop in LLVM. We look at inside the basic block in this loop, and we encode from those instructions. We encode. We have a feature representation. So we count the number of addition, the number of multiplication, load and store, packet load and store. And we model this by using linear and support vector regression. So the current way LLVM does it is just to sum up the costs for each instruction. In my opinion, that doesn't work, because there are instructions like load and store. They do not. When you only select a number, they usually use the overestimation, the maximum latency an instruction may take, which is too pessimistic. So we used an approach based on real data. And so actually all of those instructions in the end, they become a vector of weights, a weight vector. We also use some normalization that improved a lot the accuracy of the model. And what we finally got is to improve LLVM from 0.18 as a correlation factor to 0.82. So you see this distribution is much better than this one. Still we have some misprediction, but overall it's much better. So this is another case where we didn't really start. I didn't want to use machine learning here in the beginning, but when I saw the problem, I see maybe here it may work, and it really worked. It really worked because machine learning is based on real data, and instead of someone fixing the cost manually of an instruction, if you have this evaluated on real data by a machine learning approach, because in the end machine learning is a statistical approach, getting the information from real data, this improves the performance. So, and this worked on LLVM. So I'm really looking forward to publish this work so that we can also contribute to the LLVM repository with our improvements. So this was a case where we used regression. So regression means predicting one number. Okay. So before we have seen classification, now we have seen regression. So far, we haven't really used strange magic. We have used a really standard approach. What was really particular was the encoding of the problem, the way we encode, for instance, instruction into a feature vector, but the modeling was very simple. Now, and this is the last example I will show you, and this is the one I think the most challenging of the one I have seen, is the one I started discussing before, so the stencil computation example. So I already told you what a stencil computation is, and I already told you that there are some optimization we can do on stencil computation. I use it for this, a source-to-source compiler. So I use it. This is called Pathos stencil compiler. It's a compiler actually written in Java, but it produces C code, and this means that later you can use LLVM or the Intel compiler or any other compiler. So it's an approach very, very common when you want to prototype some optimization. And so the idea is, okay, we have a stencil code. I want to understand what is the best optimization and the best configuration, which means blocking factor, which is 3 numbers, a rolling factor, which is 1 more number, and the chunking factor, which is how many SIMD lines, SIMD instruction I assign to each thread. Okay, this is a parallel parameter. Is very important. It's probably the most important here, together with blocking. So start to work on this, and also state of the art is using iterative combination. So they are just trying different combination till after 1,000 iteration, which for some sense of code means like 2 hours of compilation, you finally get a good solution. That's really, it works if you have to optimize one code. But if you have many codes to optimize, clearly machine learning is better, because you build a model, then you can use the model with any other new codes. And so we worked to solve this problem, and this specific problem was a collaboration with the University of Stanford with Stefan Armon, who is is very good in machine learning. Is an expert of structural approach. So a structural approach like structural support vector machine are those typical approach you use in context where you don't have enough data. So I have seen structural learning applied, for instance, for understanding the chemical properties of materials, for material discovery. This is a case where you don't have a lot of data because you cannot go to the lab to create new materials all the time. So you understand those are scenarios where you cannot use deep learning. You will never have all this data. So practically, we encoded, we find out a way to encode those stencil and to generate stencil codes for our training data. And then we used a structural learning approach, which is called ordinal regression, which was really fitting very well in this context. And the idea of this is beyond classification or regression. This is a way to rank, to sort configuration. So the idea is to have a model that doesn't select, like classification, the best performing, doesn't predict a performance number, but it takes all the configuration and sort them out, and then you take the best performing. So step by step, a stencil code was encoded into a feature vector. We had to encode information like number of buffer, the type, which was only one between float and double, the input size, which is very important in this problem, and the shape. For the shape, we had a pattern of 0 and 1, and the 1 was marking which element was read. So we know we write in the center element, but we mark with 1 all the read element. For instance, if you have a stencil like that, we are reading from 1, 2, 3, 4, 5 points. I mark a 1 there, okay? So this is a simple way to encode stencil. We needed a domain-specific approach here for encoding our input. And we developed a stencil code generator, because I didn't really have a lot of data. And I said, but in the end, it's just a stencil. A stencil is something like a line, or an hyperplane, or an hypercube, or a Laplacian. So most common stencil code fall in one of those categories. So I create a program that creates randomly those kind of programs with different sizes and with different number of buffer and buffer types. And each of those codes, I run it and I execute it with different combination of tuning parameters. Of course, I couldn't try the whole tuning space. I just tried randomly, because the tuning space here is too big to do an exhaustive search. That's the problem. We cannot do an exhaustive search, but by testing enough parameters, tuning parameters for enough code, I hope to get a good model. And once I get the data, then the problem is, and now how do I model it? And this was very challenging, because here classification doesn't work. Classification doesn't work here because I have something like 60,000 tuning configuration, and using classification here means that I need at least 60,000 classes, one for each combination of parameters, which is crazy. I will never have enough code to call all of them. So the idea of using classification here is really bad, so it doesn't work. On the other side, I could use regression. So regression is the approach used for vectorization. There is a problem with regression. That's something I didn't tell you before. When we use regression, we are actually trying to do performance prediction. Performance prediction is one of the most complicated problems in performance modeling, in performance tuning, and is actually much more complicated than what we want to do. I don't want to know how good is. I don't want to predict the performance of the best of all my tuning configuration. I just want to know which one is the best one. Okay, I don't want to know if it takes 1 hour or half an hour to run it. I just want to know which one is the best one. So we can a bit relax our constraints. And in regression, so performance prediction for stencil is very hard, even because as you slightly change the size, the input size, the tuning, the optimal tuning changes a lot. Because so this is known for stencil. So this is a very that's why this problem is used as a test benchmark for auto tuning. It's really challenging, and doing performance prediction here is not really the best solution. So think about that. So classification means you have your samples, which means one execution on with some given parameters on a given code, and you practically mark it. And you are looking for an hyperplane if you're using support vector machine to separate those classes. We instead do something different. We are looking for a ranking, which is a way to sort those samples. So it's something like we are looking for a hyperplane for a weight vector W, which tells us that configuration D is faster than C, which is faster than A, which is faster than B. So this is the different approach. This is the different way we want to use machine learning. And it's something that when we tried, I said, wow, but this fits very well with our training data set. And in the end, it's very easy to rank our training data, and we only have to pick up the top ranked in the end. Evaluation is very fast. Training us is very fast because this is based on support vector machine with linear kernel, very fast. You don't have this long training phase like with neural network. This is very fast. So we tried this, and it was when Professor Herman from Stanford proposed me this approach. I said, but where did you take it? Because I couldn't find this. This is not known machine learning approach. So usually for image recognition, you use classification, and you can use regression for other tasks. Never heard about ordinary regression. It was actually used, I think in 2005 or early, by a professor from Cornell, Joachim Thorsten, to improve the way you rank the top 10 link in a Google query. So you do a query on Google, you have the top 10, and this professor was using click-through data to rank those 10 links by using the click-through data. And there are many similarities between those two problems. So we applied ordinary regression. So practically, suppose this is our example of training data. So we have one code with an input size. We execute it with different, for instance, in this case, with 3 different tuning configurations. Then we do it again with another input size. Then we do it again for a different code, and again with a different input size. So the idea is that if you use normal regression, you will use this rule. No? You will use the runtime. Instead used the ranking. So we create a rank for each execution, for each input, so which is a combination of code and input size. Of course, we cannot compare globally. We cannot compare tuning configuration with different codes. This is misleading, especially with different size, because of course, if you run a code with a bigger size, it will take longer time. So we encode those ranking. So we had a partial ranking actually. So we don't have a global ranking of all the configuration, but a partial ranking. And the idea is that out of those rankings, we generate inequalities. So actually, we can say that E1 is faster than E2 because it's ranked 1 instead of 2, and out of this, that E2 is faster than E3, and so forth. So in the end, what we will encode in our model are those inequalities. Okay, so this is very important because we do not we do not encode runtimes that are really high varying numbers, and they have all those problems I told you before. It's about performance prediction. We are solving a simple problem. We are trying to rank our configuration, and so there is a little bit of theory here, but I will just give you an overview. So overall, the idea is that suppose that R star is the real ranking in the training data set, we would like to calculate a ranking, so a function that is very similar to the one in the training dataset. So we would like to build a ranking R. And the problem is also, how do you know it really works? So we need something like a tau function, which is a function, I will show you later what is this tau, which is able to compare two rankings and tells you, oh, those are similar or those are not. Okay? And do this for all the code in our training data. So the approach is called ordinary regression. It can be implemented in multiple ways. We implement it with support vector machine, structural support vector machine, and this is practically an optimization problem. If you are familiar with support vector machine, probably you already recognize this formula. So it's an optimization problem. What we do is to encode our inequalities. The ij's are the inequalities in our system on our feature vector. That is the stencil instance plus the tuning setting. It's very similar to a typical classification. The difference is that we encode the inequalities, and this trade-off, the C parameter that you commonly use also in machine learning in support vector machine classification, this parameter needs to be normalized over the number of all the inequalities. So there are some mathematical things to take in account, but in the end is an SVM approach. So, and there is still one consideration, that we don't have a global ranking, we only have partial ranking, and this means that we don't really have so many inequalities. We have less inequalities generated by the single instance, so that we have to partition our training data in subsets. So, and we encode inequalities for each subset. Okay, so this is just actually a very important mathematical issue, because this improves a lot the capacity of the model. And in the end, we had very good results. So we were really surprised, because with only 8,000 point dataset, only 8,000, a very small number, 15 out of 17 benchmark performed close to the 90% of the best solution, which we got by running iterative search for hours. So this is a quality comparison. Of course, we don't know what is we cannot do exhaustive search, so we don't know if we got the best. What we did is to run exhaustive search for long time. In this case, 1024 iteration was enough. And we got a very, very good solution. We tried with different size, but we got, even with very small dataset, it worked very well. And the idea is this: when you have a new code, you practically generate the tuning vector with all the possible optimization. So 60,000 tuning vector. You run them, and this is very fast, even for 60,000 configurations, very fast. And out of them, you take the best performing one. This is your optimal solution. It was working very well. We were actually surprised, because this is a challenging problem. It was working even too much well. But we said, it converged so fast, but what's going on to the world ranking? Here we were selecting the top ranked. And to do that, okay, this is probably interesting for who of you used machine learning past, because this is something you only use with ordinary regression. How do you know? So we knew that the top ranked was good. How do you know if the world ranking was good? So we used a statistical tool. It's called Kendall Tau. Kendall Tau practically is something like, you have two rankings. You compare, you calculate how many concordant and discordant pairs you have, and then you get a coefficient, which is 1 if they are the same, 0 if they are random, if they are independent, and -1 if they are practically if one is the reverse of the other. And therefore, we calculated this Kendall tau for different training data, so different training data size. And for instance, with really few points, like less than 1,000 points, the model wasn't working properly. And we could see that all of those, so each of these line is 1 point on the training data set. And sometimes was -1 also, sometimes was 1, but you see, doesn't seem to work well. With a larger data set, training data set, so with more than 6,000 points, the approach was more stable, and we always add positive Kendall tau. So in general, this means that you need about 6,000 points to get a very good top-ranked configuration. But if you improve, if you have more data, what you are doing is to improve the overall capability of ranking of the model. Okay, so this was also very interesting, and also this is something that you don't do with other approach like classification and regression. This is something specific to ordinal regression. So the capability of rank configuration. And so this was our my first example. So this was published. I presented this in Orlando last year in IPDPS, and was really this is the case of a new machine learning approach that works very well for compilers. Okay, not something taken from other contexts. This has been designed for that. We designed this partial ranking because this was a problem we had in our training dataset. So, and so this is a first structural approach applied to compilers. So, to conclude, so I have last 5 slides. We have seen 3 application of machine learning into software optimization or compiler context. They have very different challenges. You have seen this is very different from image processing or other contexts. And what is very interesting, of course, the application, sometimes there are applications that are not really suitable for machine learning. We need to solve the problem of the training data availability. So sometimes we don't have enough data. And for that is much better support virtual machine approach like that than deep learning. We need to have to encode the input, and this sometimes requires some smart solution, like the way we encoded the stencil shapes. And the modeling. The modeling, I think also this is something that needs to be improved. We need to design smarter model designed for this context. So in general, there are many interesting solutions around for those problems. For the training data generation, I showed one for stencil code. It is very interesting, the work from Edinburgh. They used deep learning to generate code, not for modeling, to generate codes. Practically by doing getting code from, I think, from repository like GitHub and generate code. Very interesting work. To some extent, alternative to similar to mine in the way they generate code. Kernel function is another interesting solution. So with support vector machine, you can design kernel function for control flow graph, for instance. So you can really adapt your approach to the context. And I really love the idea of using structural learning, which is not simple. It requires a lot of math, but you can. So the idea of structural learning is that you can adapt your machine learning to the output structure of a problem. And I think this is beautiful because in compiler we always have structure. No, we have as an input structure like tree, graph, polyhedra, but also as an output. And for instance, one of the work, my next work I'm planning to work, so is multi-objective optimization. That is something probably new for you. And so the idea is that sometimes you don't only care about performance, but you may also care about energy or accuracy if you have an approximated approach. And the problem is you don't have only one optimal solution, but you have what is called a Pareto set, Pareto frontier of optimal solution. So this is a paper we just have accepted to CGO, so this will be presented in Vienna in February, about how to approximate OpenCL kernel. No? So in this case, we try different techniques. We also design new ones, and there are some are very good, but they do not approximate very well. Other ones that approximate a lot, but they are faster. So, for instance, it would be nice to have a compiler that produces those Pareto points as an output. And this is an example of structure. So the idea is, let's use structural learning to do that. This is an example of structure. This is my take on this. This is a personal opinion, of course. This is something I haven't tried yet with this specific problem. This paper doesn't use machine learning yet, but my idea is let's model structure in compilers. Another concluding note about the programming model. Tuning is very important with parallels, but we have many ways to write parallel program. So we have low-level approach, like you write a C program, you use automatic vectorization, this is parallel. But you may have an annotated C program, like by using OpenP. You may have domain-specific approach. You may have library. So tuning is something is a problem they have, all of them. And of course, application is very different depending on the programming model. And what is also interesting is that high-level tuning, so algorithmic choice, the way we apply parallels, or the choice, for instance, of spatial data structure in some graphics problem, they may have an interaction. They actually have an interaction with low-level tuning. So this is, I think, is the next big challenge. I have seen a group like Imperial College of London doing some interesting work in this context. So this means that you have your parallel framework, and the way the hardware you choose on the top of it, they affect the way the way the code can be optimized by a compiler. And this interaction is not trivial and requires automatic tuning. So this is, I think, is the next challenge, the next big challenge in this field. I have two related work on this. Actually, this is we have a domain-specific language for agent-based simulation. We designed it, and we are going to release the source soon, where we were planning to apply this high to low level tuning. And this is fresh news. I have a project accepted by the FG, and actually I will have probably soon an opening. If you know about good students willing to do a PhD on this topic, we will soon have an opening for a PhD studentship and for this project called Celerity is about high performance computing. We will use as a programming model SQL, which is this OpenCL extension. We are in touch also with Codeplay for this problem. So with this, I conclude my talk. So I show you a real example. The last note are more my opinion. So I want to make a strong distinction between the two. There are things I published, I tested, I tried. The last one are my view about what's going on in this field. And in general, I think tuning is something you will hear a lot in the next decades. So I think in the next year, because you will always have more complicated hardware, more parallel, more memory layers. So it is a problem that will not be solved. You will probably have more tuning problem in the future, not less. So that's why I think it's very, very important to find solution for those problems. Thank you very much for your attention. So I want to thank people who are working behind all the paper I showed you from TU Berlin, from Stanford, and Innsbruck, and the Leibniz-Raken Syndrome, that they helped me a lot on this work. And if you have any question, please ask.
Thank you, Biagio, for your presentation. Hands up who can summarize the ordinal regression example from that we see last. I think it's really complicated and it's the most scientific presentation we saw so far, but I think there's a few practical things we can take away from here. Are there any questions from the crowd already? Maybe.
I have maybe two.
Okay.
So in the first example, you said that you tried both SVMs and neural networks, but for some reason you only showed the results for the neural networks, which makes me wonder the SVM didn't work so good.
They were very similar.
They were very similar.
They were very similar performance. So like 85, 86. No, I don't remember exactly because we had different combinations. So we had best performance by using neural network, but slightly better than SVM, and using PCA has improved, principal component analysis. Yeah, this was the best.
All right. And the second question is more like principled in a way. So to me it looked like you had your training data, which were like programs and maybe some runtime programs, and then you had some way to test the like unseen code, I would expect. So, but it seemed that for sometimes it seemed that the programs you trained on were also the programs that you then used for prediction.
No.
The testing programs were never seen.
So all of those work use a different approach. So the first paper used the leave one out validation. So it means that when you are evaluating one code, you remove it from the training data.
Yeah.
Okay. The last one, instead, the training data was synthetic, so was different. So of course, this is you don't do the evaluation on the training data, otherwise it doesn't make any sense. Yeah. We only did this for calculating the Kendall tau, but this we did because it wasn't really possible to test the optimization space. We couldn't try all the possibilities, so we took the data we already had. You cannot compute the Kendall tau for the whole training data.
Okay. So because then I'd like to. So this basically implies that the codes that you see at testing time that you haven't seen during training, and the features that you manually computed, extracted
automatically, usually, yeah.
Yeah. I mean, but still manually said you're counting this number of instructions, the number of branches, and so I mean, you didn't go to the tree or anything like that, right? You just extracted like the number of instructions, I don't know, the number of branches, stuff like that, and that was like sufficient to like basically cover code that you haven't seen.
Yeah. So for the OpenCL case, OpenCL code usually are not really sophisticated. OpenCL kernel are very small, and we use some heuristics, of course, with loop, we enrolled loop and things like that. So they were. By the way, there is some degree of approximation. So for the stencil, there of course you have a DSL, so you have like sandbox. So it's very simple to get your feature. The only problem there was the stencil shape, and then we had to invent this matrix representation of the stencil shape. So it depends on your problem. You in theory, you can also use the abstract syntax tree, because the first problem I show you, we extract those operations from a tree representation, because the inspired, the intermediate representation of the Nzibe compiler is an abstract syntax tree, practically, where one node is a kernel expressing parallelism. So yeah, so we extracted from feature. We didn't really use kernel because there are more sophisticated machine learning approach for tree, like tree kernel. We haven't used it yet, but I think they may have sense for some context that I haven't investigated.
Yeah, so because that was what I was thinking. So because you in the very beginning you showed, it's actually important to like show the structure directly to your learning process, but then it seemed that you didn't need it, right? So, and now you say maybe there are some examples where actually could benefit.
I can tell you. So I used the tree, but I didn't use tree kernel. So we practically in the end flattened the representation. I think there is one other work from Edinburgh using tree, but it was for a very different problem. So now I can tell you without checking the paper. There is at least one paper I know from Cavazos, Delaware, University of Delaware, using polyhedra, so matrices, for the polyhedral model only for loop optimization. Stencil, I think this is the only approach you see in this way. There is no relative work using this stencil representation. In general, you have to adapt to the problem you have. In the case of loop, in the case of vectorization, we try to not touch too much in LLVM. We use something that is easy to plug into LLVM, and LLVM has this cost model up by basic block level with some combination of basic block. When you have control flow, we use the same. So it really depends a lot on the context, but it's hard to say it will work for any optimization. It depends.
Any more questions?
Please repeat the questions.
Okay.
I work at the database group at the TU Berlin, and so database compilers basically have the same problem. And many databases have this tuning phase where you try to select the best operators for your hardware based on the different variants of SQL and the physical operators. So is there a link between the things, or are you looking into the kinds of optimizations they do?
So the question is about the application into database scenario.
Basically operator selection and these kind of things.
So I'm not really confident with the database tuning, but whenever you have a tuning problem, so you may have algorithmic choice, you may have any kind of software optimization. What I want to say, this is now trending in the compiler fields because of parallel hardware and the increasing complexity of the hardware. But of course, there are other scenarios where probably for instance, I have seen application of auto-tuning in computer vision algorithm, and they were mixing algorithmic choice with compiler optimization. So I think there is potential, but I don't know the context.
Any more questions? So then I have a question. So if I understand it correctly, your models that you create are specific for one hardware, and they are on a very high level described abstract set of properties for this hardware to do optimizations for that. Is that right? So are you using mostly scientific computing hardware, or are you also using general purpose like CPU? Like general purpose CPU?
So the work you see here, so I started working in HPC, so I use it from C and GPU, a lot of GPU. This work, exactly this one, I'm also using, now I'm porting to ARM, because, well, now ARM is multi-core, you have neon vector instruction, so it's a very complicated hardware. It's not really, one may think, but my mobile phone has a very simple hardware. That's not true. It's very complicated, and there are tuning problems even there. So now I'm also applying this to embedded system. But the biggest challenge arises from HPC, from high performance computing.
And you had this slide, which was the greedy feature selection slide with the tables and all the number. I don't know. Maybe we can show it again.
Yeah.
Or don't know. Yeah, it was there. No, not this one. That was the performance number. Yeah, this exactly. So this is a summary of what was the most important features per hardware, right?
Yeah. So this is one hardware. This is another hardware. So,
okay. Yeah.
Okay.
So
this hardware, we had static and dynamic features.
Yeah.
So the top ranked, which means the one that if I remove has a bigger error, was the data transfer size for splittable buffer. This is the implementation detail, because the partitioning wasn't done by the compiler, and the compiler was marking the buffer which you split, and the one we have to copy after some analysis. So we were marking this as a different features, and So knowing this size was very, very important. The number two was OpenCL built-in family. And I think this was because the GPU had those, when you use trigonometrics, for instance, GPU has the sine, cosine operation on the hardware, and I think the AMD we used there, it wasn't performing very well for that. Number of branches, of course, GPU don't like number of branches. Especially at the time, now they have improved a lot, but this was a big problem, and I repeat, this is a paper published in 2013, hardware is a bit old. Floating point, scalar floating point operation and so forth. This was very important here because AMD is very good with integer, and so while you were having integer instead of float, this makes a strong distinction.
Yeah. So are these numbers somewhere like? Do you only have the numbers for the two shown hardwares, or do you have the whole database of values for all kinds of hardwares, and is it available to?
You want to know the feature list?
Yes.
I can. So if you ask me, I have it somewhere.
Okay.
I would. So for space
Is
reason,
it published somewhere?
this is not even published because in the paper you have like page limitation, and and usually you cannot put all the data. But I have it.
Okay.
Actually, I think I hope in about 1 year to have a new version of this code, because we are reproducing this code, this work in SQL.
Mm-hmm.
Originally, this was done with this in CMA compiler,
Ah.
but I'm not working there anymore, and I think they dropped the OpenCL support. They are always only using OpenP right now.
Mm-hmm.
This was a parallel compiler taking as an input OpenCL or OpenP or MPI code,
Mm-hmm.
having a parallel intermediate representation and different backend. The problem is that it was so big, it was very hard to maintain, and I think the OpenCL part is not available anymore as far as I know, but this way we are going to reproduce this work again, because this makes a lot of sense for embedded system.
Yes, exactly.
And we would like to use SQL for this OpenCL based, and it's using SQL is using an intermediate representation which is based on an LLVM IAPS. So it's a.
So I think this would not only be very interesting for the finding optimization parameters, but also for hardware software co-design. If you release let's say something for one specific platform, you probably want to know the performance properties of this platform. It could be a very good resource for people who make software for dedicated hardware.
Yeah,
So
you can also extend it with hardware features if you want to do co-design. So and this makes for co-design this makes sense. Yeah.
And it's empirical data, so it's
it's data,
as long as it's
I think it's very good to communicate idea in our field that machine learning is a good tool if you use it properly. Because there is a bit this idea of it's black box, or you're just doing this that has been done in this other field. But see, those information are very interesting. I couldn't guess before that the number of OpenCL built-in was so important for this problem. So this was very interesting.
So you still need to benchmark yourself, but maybe that's a good resource to get some initial data. Are there any more questions?
So you said you only have so many. You don't have enough data, but you auto generate the data, so you basically have as many as you want. So what's limited is too slow, perhaps.
Well, so you think about you want to execute a stencil code which takes for very big size may take 1 minute or longer. And you don't really want to spend 1 month to collect 100,000 points. And moreover, if you change hardware, you have to do the training again. So clearly, so if you want to use this in a compiler, the better is the training data you need, the better is the approach overall. I mean, you cannot reuse the data when you change the at least in the way has been used so far, machine learning. You cannot reuse the data with a different machine. So
if you would, for example, include hardware details in your training features, and you would have enough information from enough different platforms, could you then now make it portable in a way that at least you don't have to rerun the whole training again?
I think it's possible. That's in theory it's possible. Of course, the hardware features if you apply only for one of these contexts will be always the same. So you need enough hardware.
Yeah, you would have a database of different people.
Yeah, I think. I think in theory it's possible. You have to use different machine learning approaches, and probably this work from Dividity is called so the founder of this company was I think PhD in Edinburgh. So they are doing something like a collective database, but they are doing this, as far as I understand, only for the compilation flags problem. I think the amount of data you need is so huge that it's not easy. You need a lot of hardware. Then maybe so for HPC is easier, but when you go on embedded system, maybe your machine you have bad data because your machine is running something else. Also, what I didn't mention in this presentation, you must be sure your data is statistically stable, no? And when it comes with multi-threading, maybe you have to repeat your test multiple times. Maybe you may have other process doing something this you don't want to. For HPC, this is less a problem because you have a isolated machine. But in mobile systems, this is a big problem. So the nice thing is that you can also, when you support vector machine, you can, if you already know your data is unstable, you can use large margin to improve the consistency of your model. So there are some machine learning tricks you can use. But still, you have to pay attention.
You can do online updates of your model.
Yeah, there are some work on this direction. Yeah, this is also an option. Yeah.
Any more questions? So do you have volunteers already for the vectorization cost model implementation for the upstream LLVM?
Yeah, so you mean for the second work?
Yes.
Yeah, this work I'm supervising. So the first author is Angela Paul, who is part of her PhD. Mm-hmm. And I think she's doing really well. Mm-hmm. She found very interesting things in the cost model vectorization. Also some issue in the way the ARM code is vectorized with control flow graph and many interesting things. So probably not really soon, but in 3-4 months, I think we can ask her to give a presentation if you're interested.
Yeah, or to find people to implement it for for LLVM so that it's available for everybody.
But it's in LLVM. These are already in LLVM.
It is already in.
So the evaluation she did both in LLVM and GCC, but we implemented it in LLVM. Okay. Because it's much easier, of course.
Yeah.
So this is already in LLVM. So but also the other SQL work, this will be in LLVM. Okay. So there are many work in LLVM.
And she committed it upstream already?
No, she didn't commit anything yet. Okay. So it's still in the phase where you submit a paper to a conference.
Sure.
And later you push it, even because there may be problems that arise meanwhile.
Yes, sure.
And this is also part of the scientific process. No, we have to be sure of our results.
Okay. Yeah, I think that would be a very interesting thing to have a look on.
Mm-hmm.
If there's no other questions, then I would say thank you for being here and joining our meetup. And we can stay here and have a little more discussions and conversations if you like. There's a few drinks left in the fridge if you want. And I hope you all had a good night, good evening. Thank you very much.